In geometry, when we refer to an angle, we mean a union of two rays that have the same origin and that go in different directions. In trigonometry, we're going to take a more sophisticated view of angles, and we're going to take into account not only what direction the two rays go in, but how they might have gotten there, or in other words, how we could rotate one of our angles to arrive at the other one. So for every one of our angles, we're going to identify two of them, the two of them, as an initial and a terminal, meaning that we're going to start with one of them and end with the other one. So one of the angles is going to be called our initial ray, and the other will be called the terminal ray. And we're going to think about how we can go from L1, our initial ray, to L2, our terminal ray, by rotating around the point that they have in common, that is, the origin. And we can see that there are many ways that we can do this. We could do this by, say in this case, rotating counterclockwise around from L1 to L2. On the other hand, we could try rotating counterclockwise and going around the almost all the way around in a circle before arriving at the terminal ray. Or we could do something where we rotate around more than one complete time and come back to get to the terminal ray. So for us in trigonometry, an angle is not going to be just a pair of directions, two rays that are pointing in different directions, but it's going to describe a rotation. So for us, these three rotations are going to be considered three different angles. So we could think about standing on the origin, and we start off by facing in the direction of L1, and we turn to get to L2. And one way we could do that is by turning to the left, that is the counterclockwise one, just a little bit in order to get to the L2 direction, and that's this angle right here. Or we could turn to the right and spin almost all the way around to get to L2, or we could spin entirely around and a little bit more to start from looking at the direction of L1 to look in the direction of L2. And those are three different angles because they're three different sets of rotation, but they all wind up giving us the same direction. We wind up starting and ending at the same point, and so we want to give those a name. Angles with the same initial and terminal rays are called coterminal angles. So the three angles, the three red angles, the rotations that we described before, all describe three coterminal angles because they all have the same starting and ending positions. Additionally, in trigonometry, we're going to consider one angle that you don't really consider in geometry, or sometimes don't consider in geometry, the straight angle. And so for this one, we want to consider two rays that point in opposite directions with their shared vertex. And of course, there are lots of ways we could do this. We could have an angle that goes like this, or goes like this, or that goes all the way around. Maybe it goes around a couple of times. So these three red angles are all coterminal, but they give two rays rather, that go in exactly opposite directions. We're going to refer to this as a straight angle. In geometry, you typically wouldn't call this an angle. This is simply a line. But we're going to have need to refer to angles like this. It makes sense for us because it does involve a rotation. This just means rotating a full, or rather exactly halfway around the circle. Now, we could consider angles just sitting out in space, as we do a lot, but in order to use algebra to our advantage and solve numerical problems about trigonometry, we're going to need to standardize things. And the way that we're going to do that is we're going to think of angles as sitting in normal Cartesian space, that is the xy plane. The standard position for an angle is with the initial ray in the direction of the positive x-axis and with vertex at the origin. So if I have any angle sitting out here in space, let's say it looks something like this, that is going to be congruent to an angle in standard position. We're going to be able to find some angle in standard position that has the same shape and the same size as this one. So the way that we do that is we think of our standard xy plane from algebra, and whatever the initial angle was, in this case, or initial ray rather, in this case the initial ray is this one on the right. We're going to move this whole thing over and think of it as sitting in the xy plane, where we're going to put the initial ray on the positive x-axis. And then we're going to draw another ray so that the two angles that we construct are congruent, have the same shape and size. So this is what we mean by putting an angle in standard position. It means that we want to find an angle that's congruent to the one that we care about, where the initial ray is in the direction of the positive x-axis. Now, once we have that, we can start talking about standardizing things in terms of direction and measuring these angles. So, to measure angles, we're going to have two standard ways of doing them. So first one that many of us are familiar with is degrees. So one way is to use degrees. So we say that an entire revolution all the way around the circle, all the way around making an entire circle, is 360 degrees. So that means that 1 degree is 1/360th of the way around a circle. So 1 degree is a very small angle, of course, as we're familiar with, but we can label some other angles that we can work with using this measurement. Although there's something that we need to do first. Before we start measuring angles, we also have to decide on which direction of rotation is going to be considered positive rotation and which direction is going to be considered negative rotation. It turns out that in order to make our trigonometric theory consistent, we're going to want to be able to talk about positive angles and negative angles. And what that's going to mean is that positive is going to mean rotating in one direction and negative is going to mean rotating in the other one. And so the question becomes naturally, well, which way is positive and which is negative? And at the end of the day, this is a matter of convention. So by convention, counterclockwise rotation is positive, and clockwise rotation is negative. So let's think for a second about why we might choose to determine this. At first glance, because the way that our language works, this seems a little counterintuitive because we think of clockwise as sort of the default and then counterclockwise as, well, not the default. And so at first it's a little bit counterintuitive to think that counterclockwise is the positive direction. The reason why this convention may have been chosen, and I can't tell you for sure that this is the reason, but it gives one possible explanation, is to think about how we write down points in the xy plane. In the xy plane, we write down points by listing the x coordinate first and then the y coordinate, which means that the point 1, 0 is on the x-axis and the point 0, 1 is on the y-axis. And so if we think about how we would naturally want to order these 2 points, which one comes first, 1, 0 or 0, 1? And again, there's no mathematical reason to prefer one of those over the other, but it is a little bit intuitive to many people that we would look at the point 1, 0 first and then 0, 1. So it makes some sense to start with the positive x-axis because that's the coordinate we write first when we write down coordinates, and then move to the positive y-axis because that's the coordinate we use second. But that movement from the positive x-axis to the positive y-axis is in fact counterclockwise. So that might be part of the reason why we choose to use counterclockwise rotation as our positive and clockwise rotation as our negative. So let's think about this and let's sketch out a few angles to see how this goes. So the full rotation all the way around the circle, let me sketch this in, all the way around the circle in the positive direction, that is counterclockwise, by definition is 360 degrees. It has a measure of 360 degrees. And for the moment, I will go ahead and give it a positive in order to emphasize that it's positive, but of course we don't need to normally. So if going all the way around the circle is 360 degrees, what would going halfway around the circle be? Well, if all the way around the circle is 360 degrees, then halfway around the circle should have an angle measurement of half of that, or 180 degrees. Now, going from the positive x-axis to the positive y-axis along the red angle, that gives us an angle of 90 degrees. So let me go ahead and sketch in just the terminal rays for each one of these angles. So the terminal angle for 90 degrees is there. It's vertical. For 180 degrees is horizontal, off towards the right. And for 360, it's to the left, and 360 is off to the right. And they all have the same initial ray of the positive x-axis because they're all sitting in standard position, which is where we want them. So let's do a few more examples with this. Let me go ahead and take this and let's do a few more angles over here on a new set of axes. Again, we've got the positive x-axis here, we've got the positive y-axis. Now let's think about where 60 degrees would be. Well, we can think about where the various angles that we've already identified are, and we've got the vertical y-axis is 90 degrees, and so 60 degrees is less than 90 degrees, so 60 degrees would be somewhere here. An angle with measure 60 degrees would be somewhere here in the upper right-hand part of the graph between the right-hand positive x-axis and the vertical positive y-axis, and that's where an angle of 60 degrees would be, because it's between 0 degrees, which would be the angle on the positive x-axis, and 90 degrees. We call this upper right-hand part of the graph quadrant 1. We're going to wind up using the various 4 portions of the graph often to understand where angles are sitting and how they all interact with each other. And the quadrants are numbered counterclockwise, again, starting in the upper right-hand quadrant. So quadrant 1 is the upper right-hand quadrant where you have positive x coordinates and positive y coordinates for the points in that part of the graph. Quadrant 2 is in the part of the graph where x is negative and y is positive. Quadrant 1 has x and y both being positive. Quadrant 3 sits down here where x is negative and y is negative. And then quadrant 4 is where x is positive and y is negative. So let's look at a few more angles. Let's think about where negative 100 degrees would be. Now, if we want negative 100 degrees, we're still starting with the positive x-axis because we always start with the positive x-axis. But now, because we've got a negative degree measure, we're moving in the clockwise direction from that. So we're starting with the positive x-axis and moving clockwise around the origin. Now, the question is, how far do we go? Well, remember that a right angle is always 90 degrees. So this green angle right here has, we've gone the same direction. We've got a quarter of the way around the circle, but now in the negative direction. So this green angle is going to be negative 90 degrees. So if our blue angle is going to negative 100 degrees, it's going to be going somewhere more than that. So it's going to be going somewhere out here in quadrant 3. So this is our basic idea for measuring angles using degrees. We're going to start with the positive x-axis. If our degree measure is positive, we're going to rotate around in the positive direction. That is clockwise, counterclockwise. See? Almost made the mistake there. A positive angle measure moves us around counterclockwise around the graph, around the origin. A negative angle measure moves us clockwise around the origin. And 360 degrees gives us a full revolution. And negative 360 degrees gives us a full revolution in the other direction. Now we can use this knowledge that 360 degrees around gives us a full revolution in order to solve problems of the following type. Let's look at the following example. Find, let's say, 3 angles that are coterminal with 30 degrees. So, the way that we want to handle something like this, first of all, we want to sketch it out. You are going to want to start practicing sketching out these problems almost every time you do it. Trigonometry is very much an expansion of geometry, and so we're dealing with angles and eventually triangles and circles and so forth that are very visual things, and your intuition is actually very helpful when you work with it. So you should get in the habit of sketching out your work for almost every problem that you run into in trigonometry. So the first thing that we're going to want to do is to sketch out a 30-degree angle. So where is 30 degrees? We don't know specifically, but we do know that it has to be in quadrant 1. Quadrant 1 contains everything between 0 degrees, which is in the direction of the positive x-axis. So this direction here is 0 degrees, and the positive y-axis, which is the direction of 90 degrees. So if positive x-axis is 0 degrees, positive y-axis is 90 degrees, then 30 degrees is going to be somewhere in between. So we'll just sketch that out. So here's a 30-degree angle. So the 30-degree angle looks like this. And again, when we sketch that out, we're thinking of the angle that starts at the positive x-axis and moves that way. So it's actually a little better to sketch it out this way with 30 degrees down here showing the rotation. And we will stop soon putting the little arrows on the rotation symbols, but we'll keep the arc down there. We'll see how that goes. Now, if I want to find another angle that's coterminal with 30 degrees, I want to find another rotation around the origin, starting with the positive x-axis that arrives at this same angle. Well, one way of doing that would be the following. Let's try taking an angle. I'm going to start at the positive x-axis, but I'm not going to stop at the blue ray. I'm going to go all the way around, come back through, and arrive at it here. This is another angle. The red angle is a different angle. It's not the blue 30-degree angle, but it's coterminal with the blue angle. So we want to know what's the measure of this red angle. So what we think about is how many degrees has it rotated through. So if we start down here at 0, we can follow the red arc along. We see that it rotates 90 degrees, gets to 180 degrees, gets to 270 degrees down here, gets back up to 360 degrees, and then keeps going. And how much further does it go? It goes another 30 degrees. So the measure of the red angle is 360 degrees for that full circle revolution it did, plus another 30 degrees that it went for another little bit in order to get up to the blue ray, which is 30 degrees further beyond the positive x-axis. So the red angle has a measure of 390 degrees. So we've faced the same direction. The red angle points in the same direction as the blue angle, but it got there by spinning around the whole circle once and then going another 30 degrees. So the red angle has a measure of 390 degrees. All right, so that's one of our answers. 390 degrees is one of our answers, but we need two more. And there are a couple things that we can do. Well, we can take what the red angle did and do it some more. Let's suppose that we start at the positive x-axis again, keep going around. We're going to go around in the positive direction, and we're going to go all the way around the circle. And if we stopped here, then that angle, the green angle, would be the same as the red angle. But we want a different one. So let's go around again. So at this point, where I've stopped, the green angle has gone around the circle twice. It's completed 2 complete revolutions, but it still needs to do more. It still needs to go another 30 degrees. So the green angle, let's see what its measure is. It's going in the positive direction, so it's going to be positive, and it's going to be 360 degrees for the first revolution about the circle, plus another 360 degrees for the second revolution around the circle, plus 30 degrees for the blue angle in order to catch back up with what the blue angle did. And so that whole thing is going to be 720 degrees plus 30 degrees is 750 degrees. So that gives us 2. And we can actually start to see a pattern here. But before we talk about the pattern, I want to talk about the other way that we can get some more coterminal angles. Of course, we could keep rotating around over and over and over and over again, and we could keep adding 360 to the angle measure and keep getting coterminal angles. But we have another option. The other option we have is to not move in the positive direction, but in the negative. Let's say we moved in the negative direction and we wanted to go around the circle until we got an angle that was coterminal with 30 degrees, with the blue angle. We'd have this yellow angle then, and the question is, what is the yellow angle? Well, what we can see is that, first of all, it's clearly negative because it's moving clockwise around the origin. But how far does it go? We can see it doesn't actually complete a full revolution. It goes most of the way around the circle, but then stops. And it stops when it's 30 degrees away. So this missing bit measures 30 degrees. So the yellow angle is actually negative 360 degrees plus the 30 degrees. So negative 360 degrees would be all the way around the circle, but we don't get quite all the way around the circle. We need to take some of that off, but because we're going negative, in order to take some of that away, we add 30 degrees to it. And so we get negative 330 degrees. So negative 330 degrees is an angle that moves clockwise around the origin, almost all the way around, but it stops 30 degrees short of completing a full revolution and gets us to negative 330 degrees, which is coterminal with our original angle. And so the thing that I want to point out here, the pattern that we can see, is that in each case, we have added or subtracted 360 degrees from 30 degrees. So this gives us a fact that we can use, that I'll write down on the next slide. So first of all, our answer to this problem is complete when we answer 390 degrees, 750 degrees, negative 330 degrees. Now, of course, these are not the only answers. In fact, there are infinitely many possible answers to this problem, because we could keep rotating around the circle as many times as we wanted to, either in the positive direction or the negative direction. So the way that this manifests itself when we start using algebra to describe it is the following. The angles coterminal with x degrees, where x is any number, are x plus n times 360 degrees, where n is any integer. And remember, that means that n could be positive or negative. So for example, even without doing the sketch, so we could write down some angles coterminal with, let's say, 155 degrees. We could take 155 plus 360. So this would be taking n to be equal to 1. And we take 155 plus 360, which winds up giving us 415 degrees. We could take 155 degrees plus negative 2 times 360 degrees, which gives us 155 degrees minus 720 degrees, which will give us 500 and negative 565 degrees. And so forth and so on. We could, in fact, go even bigger. We could look at 155 degrees plus 10 times 360 degrees. That's going to give us another angle. That's coterminal with 155 degrees, 3,755 degrees. Now this involves running around the whole circle 10 times and then moving another 155 degrees. And that's where the n comes in here. We could think of this n as measuring approximately how many times you're moving around the circle. This doesn't always match up if your x was already more than 360 degrees or less than 360 degrees, but this fact will always work. So getting coterminal angles is simply a matter of adding or subtracting 360 degrees any number of times that you want. Now, when we want to talk about angles that aren't exactly a number of degrees, or we want to talk about angles that are smaller than a single degree, we have a couple of different options. So if we want angles smaller than 1 degree, the standard option and the best one generally to use is to use decimals. So we could talk about, say, the angle 0.76 degrees is, well, that's just 76 1/100ths of a degree. And we could always do things that way. We could talk about 95.3 degrees. And that's perfectly fine. We just use decimals as we normally do when working with these types of problems. We can also, however, use what are called minutes and seconds of arc. And this is a little bit more old-fashioned, but you still see it occasionally in some disciplines. We can also use minutes of arc and seconds of arc. And the way this works is that 1 minute of arc is denoted as 1 with a little apostrophe after it, or we sometimes call this prime in math, which is 1/60th of a degree. And now 1 second of arc is denoted with 1 and then double prime, double apostrophe. This is 1/60th of a minute, which works out to be 1/3600 degrees. So a 60th of a 60th is 1/3600th. So 1 second of arc is 1/3600ths of a degree. So if you look at some degree measurement and it says 10 degrees, 3 minutes and 19 seconds, what this means is 10 degrees plus 3/60ths of a degree plus 19 3600ths of a degree. And that's the sort of thing that you can put into a calculator to get an approximation for. Using decimals. When entering your answers into homework software, please always make sure to pay attention to how many decimal places they want and answer accordingly. Now, minutes of arc and seconds of arc, as I said, are not widely used, and they're not really that useful for us when doing math. So we're not going to use them very much. But occasionally you will, or you may see this out in the wild, and generally you'll just want to convert this into a decimal approximation using this type of transformation. Now, we have another way of measuring angles besides degrees. Degrees are nice because they're familiar. Many of us started working with degree measurements for a circle when we were very young, and we talk about doing a complete 180, meaning go halfway around a circle, turn completely around. A 360-degree view is one that's looking in every direction, so making a complete circle. And most of us are quite familiar with that. However, it turns out that degrees are in some ways a fairly artificial construct. Why do we use 360 degrees as opposed to any other number? What's the mathematical significance of 360? Well, there really isn't any. We could just as well have used 100 or 60 or any other number. So degree measure is a little bit artificial in that sense. If we ever encounter intelligent alien life, it's extremely unlikely that they will measure their angles using degrees, because our reasons for using 360 are very much historical and cultural and not inherent to the mathematics that we work with. On the other hand, there's another way of measuring angles that we're about to look at, which is inherent to the structure of the systems involved, and so it will make sense to talk about this system because it does make certain processes work, whereas degrees won't. So that is radian measure. And the idea is the following. If I take a circle centered at the origin, I'm going to take a circle centered at the origin. I could try and construct an angle in the following way. I can look at the radius of this circle. The radius is going to be some number. And as I consider various angles that move further and further out along the circle, then I can look at the length of this arc that gets created. On the exterior of the circle. And this arc starts off very small if the angle is small, and gets bigger and bigger and bigger and bigger as it goes. And eventually we're going to get to the point where this arc along the outside of the circle has a length equal to the radius of the circle. And that's going to happen at a specific point. And so we are going to call this angle right here 1 radian. So 1 radian is the angle where the arc of the circle defined by that angle has length equal to the radius of the circle. Now, 1 radian is approximately, very approximately equal to 57 degrees. And now, in fact, 1 radian is not actually equal to any rational number of degrees at all. But we're going to get a conversion between radians and degrees here very soon. 1 radian is approximately 57 degrees. And in order to get the conversion, we're going to think about, well, how many radians does it take to fulfill 1 revolution of the circle, to go all the way around the circle once? So we know that 1 revolution around the circle is 360 degrees. Now let's see how many radians it will take to do that. So we've got this distance r, another distance r, another distance r, and if you measure it as you go around, let's see if I can get this approximately right, you'll see that it takes 6 radii of the circle plus a little bit right here in order to go all the way around the circle. It's not a whole number of radii. But we can describe it by using our formula for the circumference of a circle. So we know that the circumference of the circle is pi times the diameter. That's in fact how pi is defined. Pi 3.14, etc., etc. And the diameter is equal to 2 times the radius. So that means that 1 revolution going all the way around the circle is 2 times pi radians. Because it takes 2 pi times the length of the radius to go all the way around the circle, and that corresponds to 2 pi radians. So that means that 360 degrees is the same as 2 pi radians. Or, as we more commonly use, this means that 180 degrees is equal to pi radians. This conversion factor, 180 degrees is pi radians, allows us to convert back and forth between radian measure and degree measure for any angle that we want, as long as we have its measure in one of these measurements. Now, one point I do want to make here, an interesting note, is that technically radians are not a unit per se. Technically, radians are just counting the number of radiuses that we go around a circle when we expand by an arc of that particular length. So we usually don't write any such unit. And I'll show you what I mean here on the next slide. So for example, if I've got an angle of 45 degrees and I want to convert this to radians, I want to know how many radians is 45 degrees. Well, what I can do is use the conversion factor 180 degrees over pi, or pi over 180 degrees. Now here, we think of the denominators and numerator here as being pi radians, but we don't write any sort of unit on it. That's what I meant at the end of the last slide. So to figure out which way to multiply it, to multiply this 45 by, remember that when we do a conversion factor, we want to make sure that whatever unit we're starting with up here in the numerator, degrees, should also be what we get down here. So we want the degrees on the top, on the first number, to be canceled out by the degrees in the denominator of our conversion factor. So our conversion factor we want to use is pi over 180 degrees. So 45 degrees times pi over 180 degrees, or we think pi radians over 180 degrees, is equal to 45 pi over 180. Here we've canceled out the degree units. And we always want to simplify this, and we get pi over 4. Now, we generally don't approximate these radian measures. Typically, we'll use it as a multiple of pi. The angles that we're most interested in will usually be multiples of pi, and so we want to leave it that way. So 45 degrees, we'll say, is pi over 4. Let's take another example. Let's convert the angle 5 pi over 6 to degrees. When no unit is specified, as on this 5 pi over 6, it's in radians. So we want to take 5 pi over 6. Now this one is in radians. So we want to multiply it by a conversion factor that involves radians on the bottom. Now the conversion factor that does that is 180 degrees over pi. And so we wind up with, when we multiply these together, 5 pi times 180 degrees divided by 6 pi, and then we can do some cancellation. The pi's cancel, the 6 and the 180 cancels. 180 divided by 6 is 30, and so we get 150 degrees out of that. Now, certain angles are going to wind up being very, very important to us throughout the rest of the course, and so we'll want to know their degree and radian measures often. So next I want to get some degree and radian measures for special angles. And the angles that we're going to want to look at are the ones that are multiples of 30 or 45 degrees. So we'll want to look at 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Eventually we're going to want a lot more of these, but these are enough to start with. And if we go through the conversion process that we did last time, and I encourage you to do this on your own, we will find that 0 degrees corresponds to 0 radians, 30 degrees corresponds to pi over 6 radians, 45 degrees is pi over 4 radians, that we just did, 60 degrees is pi over 3 radians, and 90 degrees is pi over 2 radians. I should also add 180 degrees, which is pi radians, 270 degrees, which is 3 pi over 2 radians, and 360 degrees, which is 2 pi radians. These angles are going to come up a lot. We're going to use them a lot. And so you're going to want to be familiar with both their degree measure and their radian measure. If you can get to the point where you can go back and forth between degree measure and radian measure on all of these quickly, it'll help you out quite a bit. Now, the last thing to note when using a calculator is that calculators usually have degree and radian mode. Because when you plug something into a calculator and you tell it give an angle, it will assume that that's a degree angle or a radian angle depending on what mode you're in. So whenever you're working a problem, always make sure that your calculator is in the correct mode. A degree mode if you're working with degrees, radian mode if you're working with radians. We will be working with both ways of measuring angles reasonably often, so you'll want to be familiar with both of those.